A building has 100 floors. One of the floors is the highest floor and egg can be dropped from without breaking. If an egg is dropped from above that floor, it will break. If it is dropped from that floor or below, it will be completely undamaged and you can drop the egg again. There are two eggs given. Find the highest floor and egg can be dropped from without breaking with as few drops as possible. So let me repeat the puzzle. A building has 100 floors. One of the floors is the highest floor and egg can be dropped from without breaking. If an egg is dropped from above that floor, it will break. If it dropped from that floor or below, it will be completely undamaged and you can drop the egg again. So there are two eggs given and you are supposed to find the highest floor and egg can be dropped from without breaking. And the important task is you have to find it with as few drops as possible. Let me explain the solution now. We can assume the eggs break at the same floor and what we are looking for is the next floor down. Our highest non-breaking floor Bn. We can also assume once an egg is broken, it's gone forever. Some solutions are pretty simple. If you don't care about how many tries it takes, you can just start dropping eggs on floor 1 and go up until you have reached the correct floor. Floor by floor would get it done, but in our worst case scenario, the egg breaks at floor 100. This means that linearly, our worst case is 100 drops to find our nth floor. To simplify, this is called brute force logic. In this approach, start from ground floor and keep going up until the egg breaks at floor X. Solution is very inefficient in case the egg doesn't break till the 99th floor. Remember, you need to minimize the number of drops in the worst case. The next approach will be binary search approach. My first thought is that we can immediately rule out binary search because we only have the 2x. With a binary search strategy, we would start with floor 50 and drop the egg from the 50th floor. If the egg breaks, we know our n is below 50. If it's intact, the floor we want is above 50. Suppose the egg breaks. The problem here is now we have lost an egg and only narrowed down our search by 50 numbers. The next step would normally be to split that 50 again and dropping the egg at floor 25th. But if it breaks, we still haven't found our floor. If it doesn't, we have only delayed the inevitable by one more step. And still no solution. The worst case scenario, we have to drop our eggs 50 times. So anyway, this binary search is not going to help in this case. Next approach will be divide a little, conquer a bit. The next solution takes a little bit of the linear approach and mixes in a little of the splitting from our binary approach. We can start off by dropping an egg at floor 10, increasing the drop floor by 10 at a time, then going back to drop one floor at a time until we find that n. So according to this approach, start from the 10th floor and go up to floors in multiples of 10. If our egg breaks at floor 10, we know n is one of the 9 floors below us. If first egg breaks, say at 20th floor, then you can check all the floors between 11th and 19th with the second egg to see which floor it will not break. If first egg breaks at 30th floor, then you can check all the floors between 21st and 29th with the second egg to see which floor it will not break. In this case, the worst case number of drops is 19. If the threshold was 99th floor, then you would have to drop the first egg 10 times and the second egg 9 times in linear fashion. Seems relatively straightforward, but we can still improve our number of drops. So in this approach, worst case, the egg drops and doesn't break until floor 100, that is 10 drops, and we drop the second egg but don't break it for floors 91 to 99. It brings our worst case drop count to 19 drops. So this is improvised solution but not the best solution. So now let's get into the best solution. The next approach can reduce our worst case scenarios by balancing the linear drops and our 10 floor drop increment. If getting to the higher floors means more drops overall, we need to decrease the drops, we need to perform linearly. We are essentially trying to make all possible scenarios and take the same number of drops to solve. We need to minimize this worst case number of drops. For that, we need to generalize the problem to have n floors. What would be the step value for the first egg? Would it still be 10? Suppose we have 200 floors, would the step value be still 10? So let's understand this in detail. The point to note here is that we are trying to minimize the worst case number of drops, which happens if the threshold is at the highest floors. So our steps should be of some value which reduces the number of drops of the first egg. Let's assume we take some step value x initially if every subsequent step is x minus 1. If we drop our first egg from floor x, 10 in our 10 floor strategy, the linear portion of our strategy is x minus 1, that is 9 in the above strategy. So our drop count is x plus x minus 1. If the egg doesn't break on the first drop, our drop count increases by 1. So we will need to remove a drop from our floor to floor drop count. The next drop should be from x minus 1 floors up. Every additional floor jump will need to have one less floor, so that when we get the linear portion of the solution, we will have one less floor to check. We continue removing one floor until we only have one floor to check. So the expression becomes x plus x minus 1 plus x minus 2 plus x minus 3 till plus 1. So this is nothing but the sum of n natural numbers, and it can be calculated using the formula x times x plus 1 divided by 2. Because there are 100 floors in our problem, we solve for x when the entire summation is equal to 100. Now solve for x. When the number of floors are different, we have to evaluate the expression for the different value. So in this case, x times x plus 1 divided by 2 equals 100. So after solving this equation, we get x equals 13.651. This means we want to start dropping from floor 14, jump up 13 floors to drop from floor 27, jump up 12 floors to drop from floor 39, and so on. So our worst case scenario is then a drop count total of 14. Let me explain this in detail. So follow the following sequence. First, drop from floor 14. If it breaks, sequentially check previous 13 floors. Maximum drops required here is 14. Else drop from floor 27 because 14 plus 13 equals 27. This is by the logic x plus x minus 1 plus x minus 2. So we are decreasing one floor in every step. So if it breaks sequentially, check previous 12 floors, that is from 26th to 15th floors. Else drop from floor 39 because 27 plus 12 equals 39. If breaks, check previous 11. Else drop from floor 50 because 39 plus 11 equals 50. If breaks, check previous 10. Else drop from floor 60. If breaks, checks previous 9. Else drop from floor 69. If breaks, checks previous 8. Else drop from floor 77. If breaks, check previous 7. Else drop from floor 84. If breaks, check previous 6. Else drop from floor 90. If breaks, check previous 5. Else drop from floor 95. If breaks, check previous 4. Else drop from floor 99. If breaks, check previous 3. Else 100 is the answer. So the total number of steps required in this case is 14. And this is the most optimal solution for this particular problem. "100 prisoners in jail are standing in a queue facing in one direction. Each prisoner is wearing a hat of color either blue or red. A prisoner can see hats of all prisoners in front of him in the queue, but cannot see his hat and hats of prisoners standing behind him. The jailer is going to ask color of each prisoner's hat starting from the last prisoner in the queue. If a prisoner tells the correct color, then is saved, otherwise executed. How many prisoners can be saved at most if they are allowed to discuss a strategy before the jailer starts asking colors of their hats? So I will repeat the puzzle. 100 prisoners in jail are standing in a queue facing in one direction. Each prisoner is wearing a hat of color either blue or red. A prisoner can see hats of all prisoners in front of him in the queue but cannot see his hat and hats of prisoners standing behind him. The jailer is going to ask color of each prisoner's hat starting from the last prisoner in queue. If a prisoner tells the correct color, then is saved, otherwise executed. How many prisoners can be saved at most if they are allowed to discuss a strategy before the jailer starts asking colors of their hats? Let me explain the solution now. This puzzle appears in a book called Are You Smart Enough to Work at Google? Quite incredibly, in February 2016, it seems to have been solved by Google's own artificial intelligence program. The solution to this puzzle is, at most 99 prisoners can be saved and the 100th prisoner has 50-50 chances of being executed. So how? So let me explain the solution in step by step. The person at the back, let's call him person number 100, will agree that if he sees an odd number of red hats, he calls out red. If he sees an even number of red hats, he calls out blue. Obviously, any similar scheme would work, but we will use this particular one. Unfortunately, this means he has a 50% chance of survival, but it guarantees everyone else. This is because he himself, that is 100th person, himself not aware of the color of the hat he is wearing, hence his survival chances is 50%. So the idea is that every prisoner counts number of red hats in front of him. Consider an example of just 5 people. Here, person 1 follows the only rule. If the first person sees an odd number of red hats, he calls out red. If he sees an even number of red hats, he calls out blue. Here he calls out blue because he sees an even number of red hats and dies. So person 2 knows that including himself, there are an even number of red hats. He looks forward and can also see an even number of red hats. This means he is wearing a blue hat. Had he been wearing a red hat, then the person behind him would have seen 3, an odd number, which he knows not to be the case. Person 3 knows that to start there were an even number of red hats. He knows that none of them have gone, that is to say nobody other than possibly the first person has declared themselves to be wearing a red hat. So including himself, there are an even number of red hats. He looks forward and can see 1 red hat, an odd number. That this has changed between him and the people in front of him means he is wearing a red hat. So next, person 4 knows that to start there were an even number of red hats. He knows 1 has gone, so including himself there is an odd number of red hats. He looks forward and counts 0, an even number of red hats. That this has changed between including and excluding him means he is wearing a red hat. Person 5 knows that to start there were an even number of red hats. He knows that 2 have gone, so including himself there is an even number of red hats. He looks forward and counts 0, an even number of red hats. That this has not changed between including and excluding him means he is wearing a blue hat. So generally someone knows whether the group of n-1 people started with an odd or an even number of red hats, and they know the number of red hats that have gone before them. If the number of red hats that have gone before them is even, then the number of red hats including them and those forward of them will be as indicated by the first person. If it is odd, it will be opposite. Knowing the odd or even nature of the number of red hats, including them and the group in front of them. They can observe the group in front of them, and if they are not the same, it must be changed by the hat they are wearing. So all but the first person survives, and he would have survived had he been wearing a blue hat. This gives us an expected survival rate of 99.5% for 100 people. We can now try a more formulated response to a larger group of 100 people. Let's analyze the responses. If 100% said red, there must have been odd number of red hats in front of him. If 99th prisoner sees odd number of red hats in front of him, then his color is blue. If the 99th prisoner sees even number of red hats in front of him, then his color is red. If 100th prisoner said blue, there must have been even number of red hats in front of him. If 99th prisoner sees odd number of red hats in front of him, then his color is red. If 99th prisoner sees even number of red hats in front of him, then his color is blue. The 98th prisoner decides his answer on the basis of answer of 99th prisoner's answer and uses the same logic. Similarly, other prisoners from 97 to 1 are saved. So all other prisoners follows the same approach what 99th prisoner followed. So that's all about the logic. Hope you understood the approach required to solve this kind of puzzle. There is an island of puzzles where numbers 1 to 9 want to cross the river. There is a single boat that can take numbers from one side to the other. However, maximum 3 numbers can go at a time, and of course, the boat cannot sail on its own, so one number must come back after reaching to another side. Also, there is a condition which states that the sum of numbers crossing at a time must be a square number. For example, 1, 2, and 3 cannot cross the river because sum of these numbers is 6, which is not square of any number 1 to 9. You need to plan trips such that minimum trips are needed. What is the minimum number of trips required for numbers 1 to 9 to cross the river? This is an interesting math puzzle. Feel free to pause the video and give it a try before checking the solution. Let me explain the solution now. Answer to this puzzle is we need only 7 trips to send all digits across the river. Let me elaborate the solution now. According to the puzzle, the sum of numbers crossing at a time must be a square number. The important thing to remember is maximum number that can be obtained using any 3 numbers with the range 1 to 9 is 24. That is by using 7, 8 and 9. So sum of 3 numbers must be 1 or 4 or 9 or 16. We can eliminate 1 and 4 because no 3 numbers add up to 1 or 4. The minimum number possible adding 3 numbers is 6, that is by using 1, 2 and 3. The correct square number that can be used to achieve the solution to this puzzle is 16, which is a square of number 4. So this is how we can achieve. In the first trip, send 2, 5, 9. Sum of these numbers is 16, which is a square of number 4. While coming back, bring back the number 9, which is a second trip. In the third trip, send 3, 4, 9, and again sum of these numbers is 16, which is a square of number 4. While coming back, bring back the number 9, which is a fourth trip. In the fifth trip, send 1, 7, 8. Sum of these numbers is again 16, which is a square of number 4. While coming back, bring back the number 1, which is a sixth trip. Finally, in seventh trip, send 1, 6, 9. Again, sum of these numbers is 16, which is a square of number 4. As we can see now, number 1 to 9 have crossed the river in only 7 trips. There can be other patterns which can be a solution to this puzzle. Do share your pattern in the comment section. A girl meets a lion and unicorn in the forest. The lion lies every Monday, Tuesday, and Wednesday, and the other days he speaks the truth. The unicorn lies on Thursdays, Fridays, and Saturdays, and the other days of the week he speaks the truth. Yesterday I was lying, the lion told the girl. So was I, said the unicorn. What day is it? Based on the statements made by the lion and the unicorn, and you are supposed to identify what is the current day. As per the puzzle, lion lies on Mondays, Tuesdays, and Wednesdays, and the unicorn, on the other hand, lies on Thursdays, Fridays, and Saturdays. Let's create a table, and table looks like this. As per the table, lion lies on Mondays, Tuesdays, and Wednesdays, and the other days lion tells the truth. The unicorn lies on Thursdays, Fridays, and Saturdays, and the other days unicorn tells the truth. So, that is on Sundays, both must be telling the truth. Suppose lion and unicorn made those statements today. The statements are: lion, yesterday I was lying, unicorn, so was I, which means yesterday I was too lying. If it was Sunday today, then lion's statement would have been lie, as lion tells truth on Saturdays. But as per data, both must be telling the truth on Sundays. So it can't be Sunday today. For rest of all days, one must be telling the truth and other must be lying. Let's consider two cases to figure out the correct answer. In the case 1, lion is lying and unicorn is truth teller. For unicorn's statement, yesterday I too was lying, to be true it must be Sunday today. But on Sunday, lion always speaks truth. And lion's statement can't be true on Sunday as concluded earlier. Hence today must be a different day. In case 2, lion is truth teller and unicorn is lying. Again, for lion's statement, yesterday I was lying, to be true it must be Thursday today. And if today is Thursday, unicorn is lying with its statement. Yesterday I too was lying, as it was Wednesday yesterday, where unicorn always tells truth on Wednesday. Hence today, on Thursday, unicorn must be lying with this statement, while lion is telling the truth. Both statements are as per behaving the given data. To simplify, on Thursday, lion tells truth, whereas unicorn lies. On Wednesday, lion is lying, which makes lion's statement, that is yesterday I was lying, true for Thursday. Unicorn tells truth on Wednesday, which makes unicorn statement false for Thursday. Since unicorn lies on Thursdays and here unicorn is lying, and it is behaving as per the given data. Thus answer to this puzzle is Thursday. This is a pretty tricky puzzle. You need to go through the solution once again to get the complete hold of the answer. How can 4 employees calculate the average of their salaries without knowing others' salary? Here 4 employees want to know the average of their salaries. They are not allowed to share their correct individual salaries. How this can be achieved, and what is the right way to solve this problem? First of all, this solution has a limitation that information is partially passed and there needs kind of some trust level. So let's say the 4 co-workers are A, B, C and D, and their individual salaries are SA, SB, SC and SD respectively. For knowing the average of their salaries without disclosing their own salaries to each other, they have to follow these steps. In the first step, A adds a random amount, say RA, to his own salary and gives that to B. B won't be able to know A's salary as he has added a random amount known to him only. In this case, B will receive the figure SA plus RA from A. In the next step, B adds a random amount, say RB, to his own salary and gives that to C without showing that to A. C won't be able to know B's or A's salary as it was added a random amount known to individuals only. Now C will get the figure SA plus RA plus SB plus RB. In the next step, C does the same and gives the final figure to D without knowing it to B. Now D will receive the figure SA plus RA plus SB plus RB plus SC plus RC. In the next step, D does the same and gives the final figure to A without showing it to C. Now A will receive the figure SA plus RA plus SB plus RB plus SC plus RC plus SD plus RD. Now A subtracts his random amount since A knows the random amount initially added and gives the final figure to B without showing that to D. B will now receive the figure SA plus SB plus RB plus SC plus RC plus SD plus RD. Here the random amount which was initially added by A is not present. In the next step, B subtracts his random amount and gives the final figure to C without showing it to A. C will receive the figure SA plus SB plus SC plus RC plus SD plus RD. In the next step, C does the same thing, that is C subtracts its random amount and gives the final figure to D without showing it to B. C will receive the figure SA plus SB plus SC plus SD plus RD. And finally, D subtracts his random amount and then the figure becomes SA plus SB plus SC plus SD. Now D knows that sum of all salaries. Now it is easy to get the average by dividing the final figure by 4, which was asked as a part of the puzzle. By following these simple steps, we can find the average of 4 employees' salary without knowing others' salary. We can apply the same technique to know the average of more than 4 people as well. We just need to remember that at every stage, only 2 people should share the figures and rest others should not be communicated. Monty Hall was the host of a game show called Let's Make a Deal, on which this puzzle is based. Puzzle states that you are on a game show and you are given the choice of 3 doors. You get to pick one door, and if you have picked the right door, you win the prize. Behind one door is a car, behind the others, goods. You pick a door, say number 1. After you have chosen a door, the game show host will not immediately open that particular door. The host will open another door that you did not pick and which he knows does not contain the prize. Assume the host opens another door, say number 3, which has a goat. He then says to you, do you want to pick door number 2? At this point, you will be given a choice. Do you want to stick with your original choice, door 1 in the example here, or do you want to choose the other unopened door, door 2 in this example? Is it to your advantage to switch your choice? Will you switch or stay with your door? This is an excellent puzzle. Think over it for some time and share your answer in the comment section. Once done, keep watching the video for the right solution. So let me explain the solution now. Here there are 3 doors. You are asked to choose one door among 3 doors, and the host, who knows what's behind the doors, opens another door, which has a goat. After this, you are asked, will you switch or stay with your door? Let us analyze what are the possibilities if you choose to switch the door instead of staying back original decision. Suppose you always choose door 1. Then host will open door 2 or door 3 behind which car is not there. There are three possibilities. In the first possibility, if the car is behind the door 1, then host will open the door 2 or door 3, and if you switch to remaining door 3 or door 2, you will find goat behind it and you will lose. And in the second possibility, if the car is behind the door 2, then host will be forced to open door 3. Now if you switch your choice to door 2 from door 1, then you will win the car behind the door. In the third possibility, if the car is behind the door 3, then host has to open the door 2 behind which goat is there. And now if you switch your selection from door 1 to door 3, then you will be winning the car. So out of three possibilities, in 2 you will be winning the game show if you switch your choice. The probability of winning the game show is 2/3. And if you stay with your first choice, then probability of having car behind selected door is 1/3. So to conclude, there is a 1/3 chance of the car being behind door number 1 and a 2/3 chance that the car isn't behind door number 1. After Monty Hall opens door number 2 to reveal a goat, there is still a 1/3 chance that the car is behind door number 1 and a 2/3 chance that the car isn't behind door number 1. A 2/3 chance that the car isn't behind door number 1 is a 2/3 chance that the car is behind door number 3. So it's better to switch the choice as it increases the probability of winning the game show from 1/3 to 2/3. So does this logic applies for any number of doors? Let's analyze. Imagine that instead of 3 doors, there are 100. All of them have goods except one, which has the car. You choose a door, say door number 23. At this point, Monty Hall opens all of the other doors except one and gives you the offer to switch to the other door. Would you switch? Now you may arrogantly think, well, maybe I actually picked the correct door on my first guess. But what's the probability that happened? It is 1/100. So there is a 99% chance that the car isn't behind the door that you picked. And if it's not behind the door that you picked, it must be behind the last door that Monty left for you. In other words, Monty has helped you by leaving one door for you to switch to that has a 99% chance of having the car behind it. So in this case, if you were to switch, you would have a 99% chance of winning the car. Hence, here also it is better to switch to choice as it increases the probability of winning the game show. These kind of problems requires a proper logical thinking to get into the correct solution. There was a magical pond between 3 temples. If anybody would wash the flowers in the pond, the flowers doubled. So once a person went to a garden, plucked some flowers and washed it in the magical pond and kept some flowers in one temple. After that, he went to the pond and washed the remaining number of flowers and kept the exact number of flowers that he kept in the first temple in the second temple. He again washed the remaining number of flowers and again kept the same number of flowers he kept in the first and second temple, in the third temple, and he was at last left with 0 flowers. So what are the number of flowers he plucked from the garden and what are the number of flowers he kept in every temple? This is a popular interview puzzle asked in several job interviews. Feel free to pause the video and give a try before checking the solution. Let me explain the solution now. According to the puzzle, there are 3 temples and 1 magical pond. If anybody would wash the flowers in that pond, the flowers doubled. In all the temples, there are exact number of flowers kept. We are supposed to find total number of flowers plucked from the garden and what are the number of flowers kept in every temple. Suppose a person start the trip with X flowers and he leave Y flowers at each temple. Here are the number of flowers person have it after each stage of the trip. So at the start, let the number of flowers he plucked be X. Now in pond, he washed X number of flowers. This will result in 2X, because if anybody would wash the flowers in that pond, the flowers doubled. Now let the number of flowers he kept in each temple be Y. Hence, at temple 1, Y number of flowers are kept. After this, number of flowers left will be 2X minus Y. Now again in pond, he washed 2X minus Y number of flowers. This will result in 2 times 2X minus Y, which is equal to 4X minus 2Y. This is because we already know if anybody would wash the flowers in that pond, the flowers doubled. So now at temple 2, Y number of flowers are kept again. After this, number of flowers left will be 4X minus 2Y minus Y, which is equal to 4X minus 3Y. Again in pond, he washed 4X minus 3Y number of flowers. This will result in 2 times of 4X minus 3Y, which is equal to 8X minus 6Y. Because we already know that if anybody would wash the flowers in that pond, the flowers doubled. Finally, at temple 3, Y number of flowers are kept. After this, number of flowers left will be 8X minus 6Y minus Y, which is equal to 8X minus 7Y. As per the puzzle, after placing flowers at the third temple, person have no flowers. This means the final equation is equal to 0. Here the final equation is 8X minus 7Y, hence 8X minus 7Y equals 0. After simplifying, X equals 7 over 8 times Y. We want to find whole number solution to this equation. As the fraction 7 over 8 cannot be reduced any further, the variable y needs to be a multiple of 8 to eliminate the denominator. The smallest value for y is 8, which means the smallest value for x is 7. So the answer is person started with 7 flowers and he left 8 flowers at each temple. So let's validate the solution now. At start, let the number of flowers he plucked is 7. In pond, he washed 7 flowers. This will result in 14, because if anybody would wash the flowers in the pond, the flowers doubled. Now the number of flowers he kept in each temple is 8. Hence at temple 1, 8 flowers are kept. After this, number of flowers left will be 14 minus 8, which is equal to 6. Now again in pond, he washed 6 flowers. That will result in 12. Because we already know if anybody would wash the flowers in that pond, the flowers doubled. Also we know that the number of flowers he kept in each temple is 8. Hence at temple 2, 8 flowers are kept. After this, number of flowers left will be 12 minus 8, which is equal to 4. Now again in pond, he washed 4 flowers. This will result in 8 because the number of flowers doubled. Finally, in temple 3, 8 flowers are kept because that is the number of flowers he kept in each temple. After this, number of flowers left will be 8 minus 8, which is equal to 0. And this is what it is expected. The solution to this puzzle is the person plucked 7 flowers from the garden and 8 he kept in every temple. So by following these simple steps, we can find the solution in less time and accurately. There are 4 prisoners. All 4 prisoners will be freed if at least one of them correctly guesses the color of the hat on his head. They can't speak to each other and they can't touch each other. However, if they take part and one of them gives a wrong answer, or none of them can work out the answer at all, then their sentences will be doubled. They are told that there are 4 hats, 2 white and 2 black. Each man will have a hat placed on his head while blindfolded. When each man is wearing a hat, the blindfolds will be removed. The prisoners will not be able to see their own hats, and the only way they can work out what color hat they are wearing will be from looking at the hats the other prisoners are wearing. All they have to do to win their freedom is for one of them to work out what color hat he is wearing. But there is a twist. To make it more interesting, three prisoners stand in a line facing a brick wall. The prisoner at the back, say A, stands on a box and can see both of the prisoners in front of him, say B and C. Prisoner B stands on a smaller box and can only see prisoner C, who in turn can only see the wall. The fourth prisoner D stands on the other side of the wall and can see nothing of the other prisoners nor his own hat. They are not allowed to turn around or converse in any way. There are no mirrors, and they all know that there are two black hats and two white hats and that there are four people. The prisoners are told that they have 5 minutes and to call out as soon as one of them thinks he knows for certain what color hat he is wearing. And remember, if just one of them gets the answer wrong, they will all have their sentences doubled. One of the prisoners says, "I know the color of my hat," and solves the riddle. Which prisoner is that? The placement of the prisoners in the room is as the following. Can you solve this riddle? Feel free to pause the video and give a try before checking the solution. Let me explain the solution now. Each one of the prisoners knows that there are 4 hats, 2 black and 2 white. If prisoner A observes that prisoner B and C have the same colored hats, he would assume that he has the opposite color and solve the riddle. However, since prisoner B and C have different colored hats, prisoner A doesn't say anything. After waiting about 4 minutes, prisoner B calls out the right answer. You can see that C is wearing a white hat. If B was wearing a white hat too, then A would have seen 2 white hats and would have known that his hat was black. As A didn't say anything, B knew that he and C must have different color hats on, and as C's hat is white, B knew that his hat must be black. Through this logical approach, prisoner B could able to answer the right hat color, and all 4 prisoners will be freed. A team of 3 people decide on a strategy for playing the following game. Each player walks into a room. On the way in, a fair coin is tossed for each player, deciding that player's hat color either red or blue. Each player can see the hat colors of the other 2 players but cannot see his own hat color. After inspecting each other's hat colors, each player decides on a response, which are one of the following. I have a red hat, or I have a blue hat, or I pass. The players' responses are recorded, but the responses are not shared until every player has recorded his response. The team wins if at least one player responds with a color and every color response correctly describes the hat color of the player making the response. In other words, the team loses if either everyone responds with I pass or someone responds with a color that is different from his hat color. What strategy should one use to maximize the team's expected chance of winning? Let me repeat the puzzle. A team of 3 people decide on a strategy for playing the following game. Each player walks into a room. On the way in, a fair coin is tossed for each player, deciding the player's hat color either red or blue. Each player can see the hat colors of the other 2 players but cannot see his own hat color. After inspecting each other's hat colors, each player decides on a response, which are one of the following. I have a red hat, or I have a blue hat, or I pass. The players' responses are recorded, but the responses are not shared until every player has recorded his response. The team wins if at least one player responds with a color and every color responds correctly describes the hat color of the player making the response. In other words, the team loses if either everyone responds with I pass or someone responds with a color that is different from his hat color. What strategy should one use to maximize the team's expected chance of winning? For example, one possible strategy is to single out one of the three players. This player will respond, I have a red hat, and the others will respond, I pass. The expected chance of winning with this strategy is 50%. Can you do better? A better solution exists for 75% chances of winning. Let me explain the solution in detail. Let the players be player A, player B, and player C. With 3 players and 2 hat colors, there are a total of 8 likely outcomes. Here are the outcomes. One special feature about the distribution is that most outcomes, that is 6 of them, include at least one hat of both colors. Here are the 6 outcomes which have at least one hat of both colors. As we can see here, in these 6 combinations, 3 combinations include 2 red color hats and other 3 combinations include 2 blue color hats. Only 2 extreme outcomes don't have at least one hat of both colors. Remaining are the ones with all red hats or all blue hats. We can analyze further. Among outcomes with both hat colors, there logically has to be 2 hats of one color. We call it as the majority color, and 1 hat of another color, we call it as the minority color. Here is the representation of majority and minority colors. Here in the outcomes, in first, second and fourth combinations, red is majority color and blue is minority color. But in third, fifth and sixth combinations, blue is majority color and red is minority color. Now, by looking at the other hats, player can identify whether they are wearing a majority color or a minority color. For instance, if a player sees both a red and blue hat, then the player must be wearing the majority color, which could be red or blue. If a player sees 2 blue or 2 red hats, then the player must be wearing the minority color, which will be the opposite color of what the player sees. Here is what players can reason among the 6 choices. If the player is wearing minority color, then he knows that the color, which will be the opposite a color of what the player sees. For example, if a player sees 2 blue or 2 red hats, then the player must be wearing the minority color, which will be the opposite color of what the player sees. Here in the first combination, if the player C is guessing the hat, now the player sees 2 red hats, then the player must be wearing the minority color, which will be the opposite color of what the player sees. Here in this case, it is blue color. In the second combination, if the player B is guessing the hat, now the player sees 2 red hats, then the player must be wearing the minority color, which will be the opposite color of what the player sees. Here in this case, it is blue color. Similarly, in the third combination, if the player A is guessing the hat, now the player sees 2 blue hats, then the player must be wearing the minority color, which will be the opposite color of what the player sees. Here in this case, it is red color. So now the idea is to get the player with the minority hat color to guess and force the other people to pass. So here is the strategy. If you see both a red and a blue hat, then pass. If you see 2 red hats, then guess blue. If you see 2 blue hats, then guess red. This strategy wins in all 6 cases with at least 1 hat of each color. It only loses in the 2 cases of all red or all blue, in which all players guess incorrectly. Here is how players would guess. Here in the first combination, player A sees 2 red hats. Then the player thinks he will be wearing the minority color, which will be the opposite color of what the player sees. Here in this case, it is blue color. Since he is wearing a red color hat, team will lose. Same happens with player B and player C. Similarly, in the fifth combination where all players wearing blue hats, here also team loses. Here in the combination, player A sees 2 blue hats. then the player thinks he will be wearing the minority color, which will be the opposite color of what the player sees. Here in this case, it is red color. Since he is wearing blue color hat, team will lose. Same happens with player B and player C. So now let's consider the second combination. Here player A see one red and one blue hat, hence player replies as I pass. Player B again see one red and one blue hat, hence player replies as I pass. Player C see two red hats, then the player thinks he will be wearing the minority color, which will be the opposite color of what the player sees. Here in this case, it is blue color and it will matches and team wins. Now let's consider the third combination. In the third combination, player A sees one red and one blue hat, hence player replies as I pass. Player B see two red hats, then the player thinks he will be wearing the minority color, which will be the opposite color of what the player sees. Here in this case, it is blue color and it will matches and team wins. Finally, player C see one red and one blue hat, hence player replies as I pass. The same logic is applied for other 4 combinations and team wins in all these combinations. So the group wins in 6 of 8 possible outcomes, a whopping 75% chance. So if you follow this strategy, there is a 75% chances of winning the game. This is a little complex puzzle, requires solid strategy in order to solve this problem. An intelligent trader travels from one place to another carrying 3 sacks having 30 coconuts each. No sack can hold more than 30 coconuts. On the way, he passes through 30 checkpoints, and on each checkpoint, he has to give 1 coconut for each sack carrying. How many coconuts are left in the end? Let me repeat the puzzle. An intelligent trader travels from one place to another carrying 3 sacks having 30 coconuts each. No sack can hold more than 30 coconuts. On the way, he passes through 30 checkpoints, and on each checkpoint, he has to give 1 coconut for each sack carrying. The question is, how many coconuts are left in the end? Let's assume that the maximum capacity of each sack is 30 coconuts. In the first view, most of the people thinks that the answer to this puzzle is 0. If you take all conditions literally, then nothing would be left. But the keyword here is intelligent trader. So you need to think according to an intelligent trader. Being an intelligent trader, he will definitely use all his intelligence to get the profit, that is by trying to save as much coconut as possible. Now I am going to explain step by step how the trader is going to save maximum coconuts possible. Initially, the trader passes through 10 checkpoints, leaving the trader with 20 coconuts per sack. It is because on every checkpoint, the trader has to give 1 coconut from each sack. This means at the end of 10 checkpoints, total left out coconuts in each sack is 20. The trick to save coconuts lies at this point. At this point, what trader does is, he distributes all coconuts from one sack into the other 2 sacks, leaving 2 sacks each filled with 30 coconuts, and 1 sack will be empty at this point. From here, at each checkpoint, trader have to give only 2 coconuts because there are only 2 sacks left. Later, trader passes through 15 more checkpoints. After passing through 15 more checkpoints, the trader now has 15 coconuts per sack, or 30 coconuts in total. At this point, trader will transfer the coconuts into 1 sack. Now the trader is left with 30 coconuts in a sack. From here, at each checkpoint, trader have to give only 1 coconut because there is only 1 sack left. By this point, 25 checkpoints already covered and remaining checkpoints are 5. Now trader will pass through the 5 remaining checkpoints, and if trader spends another 5 coconuts in other 5 checkpoints, the trader is left with 25 coconuts. Thus, answer to this puzzle is the total number of coconuts left in the end is 25. Out of 200 fish in an aquarium, 99% are red. How many red fishes must be removed in order to reduce at 98%? This is an amazing math puzzle. Though looks simple, it is more trickier than we think. Let me explain the solution now. Initially, we know that total number of fish given is 200 and 99% are red, 1% non-red. Since only red fish must be removed, indirectly the question says that number of non-red fish must be constant. As per the question, initially 1% of fish are non-red, that is 1 over 100 multiplied with 200, which is equal to 2. Currently, the percentage of red fish is 99% in the aquarium full of 200 fishes. So total red fish is equal to 198 and non-red fish equals 2. Let's say after removing X red fish, the percentage of red fish becomes 98%. This can be represented in the form of equation like this: 198 minus X over 200 minus X equals 98 over 100. 198 minus X represents number of red fishes in aquarium after removing X red fish. 200 minus X represents total number of fishes remains in aquarium, which includes non-red fishes as well. RHS represents the percentage what we need to achieve. So let's solve this equation. After simplification, equation becomes 50 times 198 minus 50x equals 49 times 200 minus 49x. So x equals 9900 minus 9800, which is equal to 100. So now x equals 100. So it is tough to imagine that we will have to remove 100 fishes out of 198 red fish to bring the percentage down by 1% in a total of 200 fishes. The point to be paid attention is that when we are removing the red fish from the aquarium, we are decreasing the total number of fishes in the aquarium. So had we been converting every red fish taken out to a non-red fish and kept them back in the aquarium, only converting 2 red fish to non-red would have brought the percentage of red fish in the aquarium down to 98%. When something is subtracted from both numerator and denominator, the overall effect on the fraction is quite small, especially if numerator and denominator are large compared to the small amount subtracted from both. In this question, if you remove 2 red fish out of the 198 red, the new percentage is 98.989898, which is quite close to the original 99%. In fact, when a small amount delta is subtracted from both numerator and denominator, the change in the value of the fraction is a small number new delta, and the increase in delta is proportional to the increase in new delta, which is also the decrease in the value of the fraction. Here the fraction value decreases approximately by 0.005%. When we decrease the number of red fish by 1, this rate of change can be calculated by differentiating the above equation. And this is another way to solve this question. So we have to remove 100 red fish. So the number of red fish in total becomes 98%. It is quite unbelievable answer. The difference of percentage is 1, but the difference in number is 100. A duck that is being chased by a fox saves itself by sitting at the center of circular pond of radius r. The duck can fly from land but cannot fly from the water. Furthermore, the fox cannot swim. The fox is 4 times faster than the duck. Assuming that the duck and fox are perfectly smart, is it possible for the duck to ever reach the edge of the pond and fly away to its escape from the ground? Let me repeat the puzzle. A duck that is being chased by a fox saves itself by sitting at the center of circular pond of radius r. The duck can fly from land but cannot fly from the water. Furthermore, the fox cannot swim. The fox is 4 times faster than the duck, assuming that the duck and fox are perfectly smart. Is it possible for the duck to ever reach the edge of the pond and fly away to its escape from the ground? Let's check the solution now. This is not a simple mathematical puzzle to solve like normal common problems. Fox in this puzzle is too fast and clever for any normal and simple strategy. One would think that the duck could swim directly away from the fox, so the duck would have to swim a distance r. The fox would have to cover half the circumference of the pond, that is pi r. Pi r because the circumference of a circle is 2 pi r, but here fox has to cover half the circumference, hence distance becomes pi r. But this strategy won't work since the fox is 4 times faster than the duck. We know that the value of pi is 3.14, thus pi into r. This is the distance which should be covered by the fox, whereas 4 into r is the distance to be covered by duck. But as we know that since the value of pi is 3.14, pi r is less than 4 into r. Hence in this strategy, by the time duck swims to near the land, fox would have already reached, which puts duck into danger. This would make it seem like it is impossible for the duck to escape, but there is a way to escape. So how could the duck make life more difficult for the fox? If the duck just tries to swim along a radius, the fox could just sit along the radius and the duck would continue to be trapped. Logic is the duck could swim in concentric circles so that the fox has to continuously run along the circumference of the pond to stay on the same radius as the duck. If the duck swims near the edge of the pond, the fox could easily keep up since they would be covering approximately the same distance and the fox is 4 times faster. But what if the duck swam closer to the center of the pond? The duck would have to cover a smaller circumference in this case and could use this strategy to put some distance between the fox and itself. Consider at a distance of r by 4 from the center of the pond, the circumference of the pond is exactly 4 times the circumference of the duck's path. Because we have considered the distance is r by 4 where r is the radius. Let the duck rotate around the pond in a circle of radius r by 4. Now fox and duck will take exact same time to make a full circle because the fox is 4 times the speed of the duck. So at a distance of r by 4 from the center of the pond, the circumference of the pond is exactly 4 times the circumference of the duck's path. Thus, to stay on the same radius as the duck, the fox would barely keep up. Now, reduce the radius the duck is circling by a very small amount. Now the fox will lag behind. He cannot stay at a position as well. Say the duck circles the pond at a distance r by 4 minus e, where e is an infinitesimal amount. So as the duck continues to swim along this radius, it would slowly gain some distance over the fox. Once the duck is able to gain 180 degrees over the fox, the duck would have to cover a distance of 3r by 4 plus e to reach the edge of the pond. So why 3r by 4 plus e? This is because the duck is already at the distance r by 4 minus e. So the distance what it has to cover to reach the land is 3r by 4, which is the remaining distance, plus e, which is an infinitesimal amount. So in the meanwhile, the fox would have to cover half the circumference of the pond, that is the 180 degrees at that point. So here, since pi r, which is a distance to be covered by the fox, is greater than 4 into 3r by 4 plus e, which is a distance to be covered by duck in the same time, since pi r, which is distance to be covered by fox, is greater than 4 into 3r by 4 plus e, which is a distance to be covered by duck. So as we clearly see that the time taken by a duck to reach the land is greater than the time taken by a fox to reach the duck at that particular point of time. So that's the reason the duck will reach the land and it will fly and escape. So in this way, the duck would be able to make it to land and fly away. So this is a fantastic puzzle. If you have not understood the solution, please watch it again. This requires a thorough understanding of the problem in order to understand how this particular solution works. In a medical laboratory, you have 240 injections, one of which is for anesthesia for a rat. If anesthesia injection is injected in a rat, it will faint in exactly 24 hours. You have 5 rats available to determine which one injection contains the anesthesia. How do you achieve this in 48 hours? To simplify this puzzle, according to this puzzle, you have 5 rats and 240 injections. Any small dosage of anesthesia takes around 24 hours to be effective on a rat. Given the nature of anesthesia, effectiveness refers to its tendency to make the rat faint. Thus, any dosage of this anesthesia should make them faint in approximately 24 hours. As the rest of 239 injections shows no effect, how will you find that particular injection which has anesthesia in it using the 5 rats you have within a period of 48 hours, that is in 2 days? This is an interesting logical puzzle asked in several job interviews. Now take your time to arrive at a solution and continue to watch further once you are done. Let me explain the solution now. Let's start solving this by naming the rats as rat 1, rat 2, rat 3, rat 4 and rat 5. Our next step is to label each injection with a number. We are using 5-digit number with 0, 1 and 2 being the only digits in them. For example, our labels will look like 110000, 10221, 12011, etc. You may have the question, why 5 digits and why only 0, 1 and 2? This is because using 3 numbers 0, 1 and 2 as 5-digit numbers, we have 3 power 5 which is equal to 243 unique ways of arranging the numbers. As we are left with 240 injections, this would give us enough ways of labeling each of them. Here is the data which shows 243 possible arrangements, of which only 240 we are going to use. So far we have labeled them. Now what are we going to do with this? Each place in the 5-digit number corresponds to each rat. Let's take the injection 12210. Here the leftmost digit, that is 1, corresponds to rat 1 and the rightmost digit, that is 0, corresponds to rat 5. A rat that is assigned with the number 1 will be given that injection on day 1, that is at the start of the first 24 hours. Similarly, a rat that is assigned the number 2 will be given the injection on day 2, that is at the start of next 24 hours. And a rat which is assigned with the number 0 will not be given that injection at all. So to make this easier, consider an injection labeled 12210. Since the leftmost digit belongs to rat 1, a small dosage of this injection will be given to rat 1 on the first day. Second place corresponds to rat 2, so another small dosage of the same injection will be given to it on day 2 because we have the digit 2 in that place. Third place belongs to rat 3 and it will be injected on day 2. Fourth place belongs to rat 4 and it will be injected on day 1. Fifth place belongs to rat 5 and the corresponding digit being 0, rat 5 will not be given this injection on both days. Our rat 5 is so unlucky that it never gets to taste it. In a similar way, we inject each of those 240 injections by following the label instructions given on them. Here, I have made a list of injections received by each rat on both days. Have a quick glance at them if you are still confused with the labeling. Now that we have injected all this, how do we know which one is the anesthesia? Let's again take the injection labeled 12210 as an example. If 12210 was the only anesthesia, rat 1 and rat 4, which received its dosage on the start of day 1, should faint after 24 hours. Rat 2 and rat 3, which received its dosage at the start of day 2, should faint when the second day ends. Finally, rat 5, which never received this dosage, will stay awake. This pattern of fainting will not be repeated in any other injection, as all of them are labeled in a unique way to make the rats faint. Remember, if any of the rats fainted at the end of day 1 itself, it will not be given any further injections as it is already under the influence of anesthesia. So at the end of 48 hours, by observing the fainting pattern of rats, we can find the anesthesia by matching the pattern to the label provided on the injection. Apart from the method which I have explained now, there is another way of arriving the solution. Split 240 injections among 5 rats and inject each of them with 48 unique dosages. Consecutive injections should be given at a regular interval of 30 minutes so that at the end of day 1, all the injection, that is 48 times 5, which is equal to 240, will be distributed among the rats. Timing should be noted while injecting each time. If any such rat was to faint, we can simply note the time at which it faints and trace back 24 hours to find the injection given at that time, which is our anesthesia. Unlike the previous method in which we observed a pattern of fainting, here we will observe only one rat getting fainted, as the injection it received wouldn't have been injected to any other rats. The issue with using the second method is that the consecutive injection interval of 30 minutes is too small to trace back to the right injection, as we can't be sure whether the effect of the drug was delayed. Of course, this method is simpler but works only when we can assure that the drug would show its effect in exactly 24 hours. Hence, it is better to go with the first method. Suppose a newly born pair of rabbits, one male, one female, are put in a field. Rabbits are able to mate at the age of 1 month, so that at the end of its second month, a female can produce another pair of rabbits. Suppose that rabbits never die and that the female always produces one new pair, one male and one female, every month from the second month on. How many pairs will there be in 1 year? Let me explain the solution now. To begin with, initially there are newly born pair of rabbits. Also, we know that newly born pair of rabbits, one male, one female, are put in a field. Rabbits are able to mate at the age of 1 month, so that at the end of its second month, a female can produce another pair of rabbits. So at the end of the first month, they mate, but there will be only one pair. It is because rabbits are able to mate at the age of 1 month, so that at the end of its second month only, a female can produce another pair of rabbits. At the end of the second month, the female produces a new pair, so now there are two pairs of rabbits in the field. So at the end of the second month, there are two pairs. At the end of the third month, the original female produces a second pair, making three pairs in all in the field. This is because it is given in the question that rabbits never die and that the female always produces one new pair, that is one male, one female, every month from the second month on. So at the end of the third month, there are three pairs. Now at the end of the fourth month, the original female has produced yet another new pair. The female born 2 months ago produces her first pair also, making five pairs. So at the end of fourth month, there are five pairs. Now at the end of fifth month, the original female has produced yet another new pair. The female born 3 months ago produces her second pair. The female born 2 months ago produces her first pair, making eight pairs. So at the end of the fifth month, there are eight pairs. This continues, but the problem is it is difficult to keep the track and solve this problem like this. Let's check, is there a pattern to generalize the solution? So pattern is, initially there is one pair, at the end of first month still there is one pair, at the end of second month there are two pairs, at the end of third month there are three pairs, after 4 months there are five pairs, after fifth month there are eight pairs, and this continues. And this is the sequence of numbers which famously called the Fibonacci sequence. In the Fibonacci sequence, the next number is found by adding up the two numbers before it. Here is a first 13 Fibonacci numbers. As we can clearly see that here the first two numbers are 0 and 1. The next number is found by adding up the two numbers. Here the first two numbers are 0 and 1. Next number 1 is found by adding the two numbers before that. That is 0 plus 1 equals 1. The next number 2 is found by adding the two numbers before it. That is 1 plus 1 equals 2. The next number 3 is found by adding the two numbers before it, that is 1 plus 2 equals 3. And the next number 5 is found by adding the two numbers before it, that is 2 plus 3 equals 5, and this continues. This puzzle follows the Fibonacci sequence starting with 1. Here is the sequence which represents the number of pairs present after 1 year. So as we can clearly see that there are 233 pairs of rabbits present after 1 year with this logic. Thus, answer to this puzzle is 233 pairs of rabbits. There are 233 pairs which will be there in 1 year. For your information, Fibonacci sequence was first discovered by Italian mathematician Fibonacci, also known as Leonardo Bonacci. The original problem that Fibonacci investigated was in the year 1201, and it was about how fast rabbits could breed in ideal circumstances. A stick 100 units long needs to be cut into 100 unit pieces. What is the minimum number of cuts required if you are allowed to cut several stick pieces at the same time? This is an interesting interview puzzle. Don't come to conclusion immediately. This requires a proper logical thinking to find the correct solution. Let me explain the solution now in step by step. The minimum number of cuts needed is 7. First, each cut can at most double the number of pieces you have. Therefore, you will need to make at least 7 cuts. This is because 2 power 6 equals 64, which is less than 100, while 2 power 7 equals 128, which is greater than 100. Let me explain now how 7 cuts suffices to cut 100 units long stick into 100 unit pieces. The following sequence of cuts works. In the first step, cut at 64 units from the left, that is, cut the stick into a length of 64 units and a length of 36 units. In the second step, lay your two pieces on top of each other, align at the left, and cut it 32 units from the left. It means in this step, lay the pieces so that the left ends line up, and then cut so that you have 3 pieces of length 32 and 1 piece of length 4. In all future cuts, we will also start by laying the pieces so that their left ends line up. So in the third step, Lay all your pieces on top of each other, aligned at the left, and cut it 16 units from the left, which means cut the pieces into 6 pieces of length 16 and 1 piece of length 4. In this step, we do not actually cut the piece of length 4. In the fourth step, lay all your pieces on top of each other, aligned at the left, and cut at 8 units from the left, which means cut the pieces into 12 pieces of length 8 and 1 piece of length 4. In the fifth step, lay all your pieces on top of each other, aligned at the left, and cut at 4 units from the left. Cut the pieces into 25 pieces of length 4. In the sixth step, cut the 25 pieces into 50 pieces of length 2. In the final step, cut the 50 pieces into 100 pieces of length 1. This procedure uses 7 cuts. To see that 6 or less cuts cannot solve the problem, note that a cut can at most double the number of pieces, so after 6 cuts, you cannot have more than 64 pieces. So answer to this puzzle is there are 7 cuts required to cut 100 units long stick into 100 units pieces. I believe that this algorithm of always cutting the largest power of 2, which is smaller than the largest pieces, will be optimal in general, not just for 100 pieces. How many diagonals can be drawn by joining the vertices of an octagon? Let me repeat the question. How many diagonals can be drawn by joining the vertices of an octagon? Let me explain the solution now. Octagon is 8-sided polygon. If you draw an octagon, select one vertex and construct each diagonal from this vertex. You will see there are 5 such diagonals. Thus, for each of the 8 vertices, you can draw 5 diagonals, and hence there can be 5 times 8, which equals to 40 diagonals. But remember, each diagonal is counted twice, once from each of its ends. Thus, there are 20 diagonals in a regular octagon. So to summarize, each point on the octagon can be connected to 8 minus 3 points. This is because you cannot draw diagonal by joining the adjacent vertex. Hence, we need to subtract 3 vertices. So each point can form 5 diagonals. So we get 40 in all. However, this includes similar pairs, that is 1, 6, 6, 1, 2, 4, 4, 2, etc. So we divide this by 2. So answer is 20. We can generalize the solution for any polygon. If n is the number of vertices, we can derive the formula. To draw a diagonal, you have to select 2 vertices out of n. But you cannot draw diagonal by joining the adjacent vertex. Hence, number of diagonals can be calculated using the technique of combination. Number of diagonals equals nc2 minus n, where n is the number of sides of the polygon. So for octagon, n equals 8. Hence, number of diagonals equals 8c2 minus 8. So 8c2 is nothing but 8 times 7 divided by 2 times 1. So after solving this, the expression becomes 28 minus 8, which is equal to 20. There is another way which is easier compared to this technique. The number of diagonals of an n-sided polygon can also be calculated using the formula n times n minus 3 over 2. For example, in a square, there are 4 vertices. In this case, n becomes 4. Hence, after substituting, number of diagonals possible in square is 4 times 4 minus 3 over 2, which is equal to 2. Similarly, in octagon, there are 8 vertices. Hence, n is 8. After substituting, expression becomes 8 times 8 minus 3 divided by 2. After solving this expression, the solution is 20. Just remember this formula, that is n times n minus 3 over 2. You can find number of diagonals in any polygon in less than 5 seconds. You need to fill in the gaps with the digits from 1 to 9 so that the equation makes sense. Here the colon means divide. Follow the order of operations, multiply first, then division, addition and subtraction last. There is no complicated maths involved, only basic arithmetic, but it's not an easy one. This problem is difficult even for adults good at math. All you need to do is place the digits from 1 to 9 in the grid. The challenge was to fill in the above snake with the digits 1 to 9 using each digit only once. The colon means divide and you must follow the standard order of operations, meaning that multiplication division comes before addition subtraction. So the best way to solve this problem is through forming equation. Rewrite the snake as an equation. There are 9 gaps. Fill the gaps from A to I as follows. Now equation can be written as A plus 13b over c plus d plus 12e minus f minus 11 plus gh over I minus 10, which is equal to 66. We are trying to find A to I, which we know are some combination of the digits 1 to 9. Before we even look for a solution, consider the total number of ways we could fill in the snake. There are 362,880 possible combinations of the digits 1 to 9 placed in 9 slots. But we can solve this problem easily by simplifying the equation. So we can simplify the equation to A plus 13b over c plus d plus 12e minus f plus gh over I equals 66 plus 11 plus 10, which is equal to 87. So after simplifying this equation, the equation becomes A plus d minus f plus 13b over c plus 12e plus gh over I equals 87. From here we can assume that b over c and gh over I will be whole numbers, and also that we don't want 13b over c to be too big. Knowing this, we start plugging numbers in and seeing where we get to. There is more than one solution. There are many different guesses that will lead to the right number. There are over 100 solutions to this particular problem. To keep the term 13b over c as small as we can, let b equals 2 and c equals 1, which gets us to A plus d minus f plus 26 plus 12e plus gh over I equals 87. And after simplifying, the equation becomes A plus d minus f plus 12e plus gh over I equals 61. The numbers remaining are the digits from 3 to 9. They include the prime numbers 3, 5 and 7. Let's get rid of them as SAP so they don't complicate the other terms. Let's put A equals 3, D equals 5 and F equals 7, which leaves us with 3 plus 5 minus 7 plus 12e plus gh over I, which is equal to 61, or 12e plus gh over I equals 60. The numbers remaining are 4, 6, 8, 9. Playing around with these gets us E equals 4, G equals 9, H equals 8, I equals 6. After substituting, the equation becomes 48 plus 72 over 6 equals 48 plus 12, which is equal to 60. Now we have filled all the gaps. After filling, snake looks like this. And of course it makes sense. There are some puzzles that you solve with a flash of insight, and some others like this one where there is no alternative but trial and error. Both kinds can be very satisfying to solve. John has 3 cakes. One cake is poisoned and he knows which one. What yes no question can you ask John to find out which cake is poisoned? This particular puzzle can have multiple interpretations. Let me explain the solution, which I think is the best solution. I have taken this solution from multiple sources, and please check the description section for more details. Let's make a couple of assumptions to answer this puzzle. The first one is that we are allowed to cut the cake, and second one is that John says the truth only among the two options, yes or no. So we have three pieces of cakes, say A, B, C. Let us cut the cake C into two equal portions, say C1 and C2. Now put C1 with A and C2 with B. So we have now two segments of cake pieces, that is AC1 and BC2. Now our question to John is, John, is AC1 more poisonous than BC2? If John says yes, that means A is poisoned, throw it out and eat B, C1 and C2. A is poisonous because A is larger in size compared to C1. If John says no, that means two options. First option is AC1 is less poisonous or BC2 is more poisonous. Second option is AC1 and BC2 are equally poisonous. Here it is clear that A is not poisonous. In this case, I suggest we better don't go for any adventures, eat the piece A, leaving B and C for John. In any case, he can't eat both. He would eat only the pure cake and would definitely throw away the poisonous one. Again, here there is no clear guarantee that poisonous cake is identified, but at least this will provide us the logical conclusion. Let me explain another interesting interpretation. According to this interpretation, one question is sufficient to finding a single non-poisonous cake, but one question is insufficient to determine the poisonous cake. Let's A, B and C be a labeling of the cakes. If you only have option to ask one question and can take no other action, there is no such question. A yes/no question gives you one bit of information. You need two bits of information to distinguish the poisonous cake from the non-poisonous cakes. As I have already mentioned, one question is sufficient to finding a single non-poisonous cake. Let the cakes be labeled A, B and C as I have already mentioned. You can then ask the question, is the poisonous cake either A or B? If the answer is yes, then we know that the cake C is non-poisonous. If the answer is no, then you know both cakes A and B are non-poisonous. Note that this question is insufficient to determine the poison cake. If the answer to the question is yes, then all you know is that either A or B is poisonous, but not which one. You would need an additional question to determine that. So there is no single correct answer which can be a solution to this riddle. Do share your answer in the comment section. There was a prison consisting of 1000 cells numbered from 1 to 1000. Each cell can be marked with plus or minus sign. Initially, all cells were marked with minus sign. From days 1 to 1000, the jailer toggles marks on the cell from plus to minus or vice versa. On the ith day, the signs on cells that are multiples of I get toggled. Now in the process of verification on 1001th day, all cells marked with plus signs are opened. Can you identify the cell numbers with plus sign? This is an interesting puzzle which is frequently asked during job interviews. If you have not understood the question, go through it again. Feel free to pause the video and give a try before checking the solution. Let me explain the solution now. It is given that in the puzzle, there was a prison consisting of 1000 cells numbered from 1 to 1000. Each cell can be marked with plus or minus sign. Initially, all cells were marked with minus sign. From days 1 to 1000, the jailer toggles marks on the cell from plus to minus or vice versa. It is also given that jailer will toggle the cell on certain condition that if the day number is a multiple of cell number, then the cell is toggled. For example, on 5th day, cell numbers 5, 10, 15, so on are toggled because here day number is multiple of cell numbers. Let's check now what happens on different days from the beginning. On the first day, jailer toggles all cells because all cell numbers are factors of 1. On the second day, he will toggle the cell numbers which are factors of 2, that is 2, 4, 6, 8, etc. Similarly, on the third day, jailer will toggle the cell numbers which are factors of 3, that is 3, 6, 9, 12. Similarly, on the fourth day, jailer will toggle the cell numbers which are factors of 4, that is 4, 8, 12, 16, etc. And this step repeats till 1000th day. A cell gets toggled as many times as the number of divisor it has. Now consider some random number. For example, let's take cell number 20. Let's see on which days this cell number is toggled. How to find it? This is simple. Just find the factors of the cell number and those are the days that cell will be toggled. Factors of 20 are 1, 2, 4, 5, 10 and 20. Hence it gets toggled on days 1, 2, 4, 5, 10 and 20. Now important observation is that we can see that divisors come in pairs, like 20 equals 1 times 20, which is equal to 2 times 10, which is equal to 4 times 5. We can see that total number of divisor is even. If the divisor is even, then obviously the cell number will be marked with minus sign since initial marking on the cell is minus. Let's consider one more example, cell number 24. Factors of 24 are 1, 2, 3, 4, 6, 8, 12 and 24. Cell number 24 is toggled on days 1, 2, 3, 4, 6, 8, 12 and 24. Now divisors comes in pairs like 24 equals 1 times 24, 2 times 12, 3 times 8, 4 times 6. So the total number of divisors is even. If the divisor is even, then obviously the cell number will be marked with minus sign since initial marking on the cell is minus. Now next big question is, does this hold good for all numbers? Answer is no. This trend is not followed if the number is a perfect square. In perfect square, total number of divisors will become odd. For example, 36. Their factors are 1, 2, 3, 4, 6, 9, 12, 18, 36. Clearly here the number of factors are odd. When the number of divisors are odd, then cell number will end up with marking plus. Hence the answer is all cell numbers with perfect square. So these cells are 1, 4, 9, 16, 25, 36, 49 and so on. Here is the list of all cell numbers which will be marked plus on 1001th day, and these cells will be opened on the same day.
On a circle, there are 2014 light bulbs, 2 are on and 2012 are off. You can choose any bulb and change the neighbor state from on to off or from off to on. Doing so, can we get all 2014 light bulbs on? If yes, how? So let me repeat the puzzle. On a circle, there are 2014 light bulbs. 2 are on state and remaining 2012 are in off state. You can choose any bulb and change the neighbor state from on to off or from off to on. Remember, if you select any bulb, you can change the state of the neighboring bulbs only. Doing so, can we get all 2014 light bulbs on? If yes, how? This puzzle is a perfect example which requires out-of-box thinking. Most of the students or candidates give up solving this problem, and most of the time they end up answering unrealistic answers for the puzzle. If you think that it is not possible to get all 2014 light bulbs on, then you are wrong. Yes, it is possible to get all 2014 light bulbs on. Let's look at the most logical way of solving this kind of puzzles. For the convenience, label 2014 bulbs from B1 to B2014. First and foremost, the most important point is the position of the light bulbs, which is on state is not given. So we assume that they are adjacent and make sure that you are naming the bulbs from here. This is the logic you must remember for this puzzle. That is, the two light bulbs which is in on state, which is mentioned in the puzzle, their positions are not given. So what we do is we assume that they are adjacent, and we will make sure that when we are naming the bulbs, we are starting from this particular point. So example like this. We will start naming the bulbs from the bulbs which are in on state. For example, here B1 and B2 will be in the on state. From B3 till B2014, they will be in the off state. Also, it is given in the question, that is, they are placed in a circular path. Now, since 2 bulb is in on state and remaining 2012 bulbs are in off state, clearly all 2012 bulbs which is in off state are adjacent. Now we will operate on these 2012 bulbs like this. Create a group of 4 off bulbs. We can choose any off bulb apart from the one next to on bulb and able to make 2 bulb adjacent to it in on state. Now choose the third bulb which we just turn in on state and make 2 more bulbs in on state. So clearly we can make 4 adjacent bulbs in on state. Let's understand with an example. First, create a group of 4 bulbs with B3, B4, B5, B6. Remember, B1, B2 are already in on state. At starting, all 4 bulbs are in off state. First, choose second bulb in the group and turn neighboring bulbs 1 and 3 in on state. This looks like this. Now choose third bulb and turn neighboring bulbs 2 and 4 in on state. By doing this, all 4 bulbs are in on state. Once this is done, consider another group adjacent to group 1 and call it group 2 with B7, B8, B9, B10 bulbs. At starting, as we know, all 4 bulbs are in off state. First, choose second bulb in the group 2 and turn neighboring bulbs 1 and 3 in on state, and this looks like this. Now choose third bulb and turn neighboring bulbs 2 and 4 in on state. By doing this, all 4 bulbs are in on state in group 2 as well. By repeating these steps, we can turn all 2012 bulbs into on state. Since there are 2012 bulbs, we have to create 503 groups. 503 is because 4 into 503, which will be resulting in 2012. And by repeating the above steps which I have already discussed, we can turn all 2012 bulbs in on state.